Hi, I'm Kevin Shaw. On devices that use gamma, so that's 709 televisions and DCI standard dynamic range projection, they all use gamma as their transfer function. And with those devices, we color correct or color grade an image to a peak brightness. But that peak brightness is not defined in the mastering display. It's defined by the end display. Right? So if I grade something at reference white, which is 100 nits, and I take it home and put it on my TV that's 200 nits, then what happens is the image scales and things that were 100 nits are now 200 nits. And so what we have is this relationship where when we grade it, we're creating relative values, and those relative values depend on the end display, not on the reference display. So somebody might have a television at 300 nits and they're going to see everything brighter than on a television that's maybe 80 or 100 nits. So we lose control a little bit at the display stage. Now, I've heard people say, oh, but that's great because if I'm in a bright room, I can just increase the brightness. Well, you can just increase the brightness, but you are changing the perceptual effects of the image. Because in calibration, if we are in a bright room, we can make the whites brighter, but the thing that we actually adjust to compensate for the brighter room setting is the contrast. So we change from gamma 2.4 to gamma 2.2 if the room is brighter. Or if the room is darker, as in a cinema situation, we change the gamma to 2.6. And so devices generally don't change the gamma. They generally change the brightness, and that changes the perception of the image. So it does scale, but it's not a very accurate way of scaling. That's just how it is. In contrast, the PQ devices have a fixed code value for a fixed brightness. So if I go back to the same example and I grade something on a PQ device to be 100 nits, well, 100 nits has a code value of 520. If I then put it on a 200 nit, 300 nit, 600 nit, 4000 nit television, it will still play at 100 nits. It won't scale based on the TV being brighter. And that gives us back a lot more control, right? So PQ is based on just noticeable differences. So each step, each digital change, each code value represents a just noticeable difference to an observer. In other words, it's the most efficient use of bits for the human visual system. And so a 1000 nit display would need at least 10 stops of dynamic range compared to 6 stops for a standard dynamic range display. HLG is slightly different because it uses gamma up to diffuse white, and therefore it still scales according to brightness. And just like the gamma world, in order for it to scale accurately, we have to change the gamma function. So do HDR formats ever scale or tone map? Absolutely. They do scale and they do tone map, and they have to because we master to a minimum of 1000 nits. But most televisions are significantly less than that. So if we don't scale it, they will just clip and lose out all these extra levels of information that we're trying to map in. So HDR formats, all of them, have to scale according to brightness, but going downwards rather than going upwards. Going upwards, they should lock off. But going downwards, we need to scale them so that we can see everything that we would have seen had it been on a 1000 nit display. HLG does it by using gamma and a log curve so that it can indeed adapt by itself. But the PQ curve does it through metadata. And there are two types. There's static metadata, where you have one set of values for the whole program, which is a bit of a compromise. Or you can have dynamic metadata, which can scale on a scene by scene, even a frame by frame basis if necessary. so that every scene gets the best possible tone map. And that metadata, that tone mapping, is controlled by the finishing colorist. So the person that creates the images also controls how the tone mapping happens. And so that's great, because that means that even on a consumer device, the best possible tone map is being applied. And the formats that have dynamic metadata are, first of all, of course, Dolby Vision. That was the first one. And then HDR Vivid, which is used mainly in China, and HDR10 Plus, which is the Samsung format for dynamic metadata. So all of those different metadata, but they all basically work in the same way. And they will scale or tone map from whatever the display master is all the way down to the equivalent of an SDR device. Another thing that I've heard people say is that PQ is inefficient, doesn't use the bits properly. And that couldn't be further from the truth, because the whole point of the PQ display is that it's tailored to match human vision. So the argument kind of goes, well, you've got 10,000 nits, and of those 10,000 nits, most of the picture is still going to be under 100 nits. So that's 1% of your dynamic range is where 90% of the picture is. And that's true. The bit that's missing is that on the old displays, which were 8 bits, you had 256 steps to describe that 100 nits of information. On a 10-bit display with a PQ curve, 512 of the code values are applied to that first 1%, that first 100 nits. So actually there's twice as many bits in a 10-bit PQ curve as there ever were in the 8-bit SDR world. And then for 1,000 nits, which is what we currently master HDR to, that takes up 75% of the code values. So that's 10% of the total range, but 75% of the code values. 4,000 nits, that takes up 92% of the code values. And that last 6,000 nits only gets around 100 code values. That seems quite extreme, but that's the way the human eye works. We see a lot of things in the dark, in the shadows. We see much less in those very bright highlights. You stare at the sun, you don't see any detail in it, and you probably be, blind for a few minutes as well. So we don't see a lot of information in the highlights, so there's no point in wasting bits there. We put all the bits where they count. And in that way, the PQ curve is much more efficient than a gamma curve, which rolls off into very few code values. So actually, PQ is extremely efficient in terms of bit depth. We talked a bit about display gamuts before. So there are 3 display gamuts that we work with today. There's the 709, which is the smallest gamut. That's based on the old cathode ray tubes from 30 years ago. Well, I say 30 years ago, but of course they go back some 70, 80 years. Then we have Digital Cinema P3, which is based on the DLP Texas Instrument chip. And it's a little bit bigger than 709, but honestly not that much bigger. And then we have this 2020 space, which in my view is not really the goal to fill the 2020 gamut. The idea of the 2020 gamut is that it's a container that all other gamuts fit inside. So it's the largest RGB primary triangle that you could create, and therefore it should be good for not just P3, but perhaps a bigger color gamut so that we can put more saturated colors on there. But don't be misled by that. That doesn't mean that just because we can't do 2020 that we don't get more colors. We do get more colors because, remember, color gamuts are a volume, not simply a 2-dimensional triangle. And in the color volume, there's a lot of extra colors that come from brighter colors rather than more saturated colors. I'd like to thank ASUS for both the ProArt PA32 UCDM and the PA27 USD. Both of these are quantum dot OLED displays, and so they are part of this new ecosystem, like I said, that can work on set, in color grading, and in the home. Thank you very much, and I look forward to seeing you on the next video.